put G2 instead of G1. G2 R prime minus G2 of R prime gradient prime G2 R prime. Okay, so this is for region 2. What is the physical meaning of this equation? Why is it that you have this zero thing over here? Why is it that you have this zero thing over there? Okay. What it says is that you have this integral. This integral corresponds to some kind of a force. You have a surface S. So there are two kinds of sources apparently. One kind of source radiate with the ordinary Green's function. You can think of this as sources on the surface that radiate using this Green's function. The other kind of source, okay, would radiate away from the surface R prime using this gradient of the Green's function. Okay, what is the meaning of those? You can think of this as a monopole Green's function. Okay, and then you can call this kind of sources here as due to monolayer sources or monopole layer sources. Okay, and the other one, actually there's an n prime dot gradient prime here. You can think of this as dipole sources. And where are the dipoles and how are they oriented on the surface from that equation? How are they oriented? Where are the dipoles pointing if they are reading through this kind of Green's function? How are the dipoles like on the surface? Can you see a physical picture? This is how the dipoles are like. Yes? Yes, this is correct. This is correct. Whether they're positive or negative depends on the sign of this thing though. Okay? But they are corresponding to dipoles pointing in the n-hat direction. There's the meaning of this, right? If you have a dipole pointing in the n-hat direction, this is the kind of field it produces. Okay, if you differentiate the monopole, you get a dipole. Okay, some people call this a double layer source, monolayer source. I call this a monopole layer source. This is a dipole layer source. Okay, some people call it double layer. I think dipole layer is a more appropriate name. Okay. And which one of these sources are the sources that produces this discontinuity? Apparently this is continuous. This first term here is just this term. And it doesn't matter where R and R prime are, this has to be a continuous function of R after we do the swapping of the R and R prime indices. This has to be a continuous function. Okay. But then this left-hand side has a discontinuity. It abruptly jumps from a non-zero value to a zero value when you cross the boundary. That is, if your observation point is inside, over here, outside you see phi1. Okay, there's some source Q over here. You see phi1. Phi1 is a contribution from the incident field, okay, plus the scattered field. The scattered field can be thought of as monolayer sources and dipole layer sources on the surface of the object. They contribute to that. But if you're over here, you see no field. So one of these two must be discontinuous. They must have a jump discontinuity. So of the monolayer source, compared to the dipole layer source, which one is the one that would produce the discontinuity? Yes? Double layer. Why?
The have a gradient of the Green's function that's bound to be
gradient of the Green's function, right?
Yeah.
That actually is what produces the discontinuity. So if you have a monolayer source, like say if you imagine a layer of charge, the potential, very near to it, we can just talk about potential. So the electrostatic potential or something like this is positive on both sides. But if you have a dipole layer, the potential must be 0 right here. Okay? So the potential goes like this, go to 0, goes like that. This is the sketch of potential around a dipole layer, a sketch of potential around a monolayer. Okay? So the potential is discontinuous across the dipole layer. So this is the term that produces the dipole layer and the discontinuity. You can actually mathematically prove it too. If you evaluate this, you find that this actually gives you the discontinuity. And you have to be careful on evaluating this integral, because the gradient of the Green's function gives you something like 1 over r squared near the surface. And actually convergence is not guaranteed. You have to do residual integration, which I will not go into. It's written up in my book as to how to do this kind of integration. So if you are in region 1, and your observation point is very close to that surface, in order to evaluate the field, that it's better to detour around the surface and do an integration that looks something like that. If you're in region 2, and you're very close to the surface, it's better to detour the surface in this manner. And then actually let the deformed surface shrink to 0. You find that this value is actually different. You find that this value is actually different from this value. Okay. Depending on whether you're inside the surface or outside the surface. In one case, you're outside the surface if you do this kind of deformation. In this case, you're always inside the surface. In that case, you will always get 0. The other case, you get phi1. And the discontinuity comes from this term over here. Because it has a 1 over r squared thing, it contributes a residual term that has a jump discontinuity. Okay? Same thing for this thing over here. And this thing over here is due to the fact that the monolayer source, like if you look at this picture, okay, the monolayer and the dipole layer sources are additive on the left, they are canceling each other on the right. So it's actually these two terms that are canceling each other in region 2. And these two terms are additive and add to phi1 in region 1. Okay, this is a very simple pictorial illustration of that physics. But that's actually what is going on. Okay? And the fact that they cancel each other, these two terms are canceling each other. They are not actually canceling each other. They also cancel the incident field as well. Cancel everything. These two terms cancels the incident field in region 2 as well. Okay, they produce the discontinuity and cancel each other. And they produce the scattered field in region 1. So this is called the extinction theory. And this is more obvious in the sense that there's no source in region 2. Okay, these two terms cancel each other in region 1 and add to each other in region 2. Okay, this is called extinction theory. And they extinct each other. Are there any questions so far? So everything is clear, right? The physics is also very clear. So we know what is happening. And sometimes people would like to evaluate this term not in region 1, not in region 2, halfway in between. Okay, halfway in between. Then halfway in between, you can prove that it gives you this value, half people. That is, if you put the observation point right on the surface. And similarly, this one too. If in region 2 you get this one, in region 1 you get this one. If you are right on the surface, what is the value? Then you can show that if right on the surface, then the value is half phi2, somewhere in between. So this is a step discontinuity the right end where the step discontinuity is, it assumes the value half. In that case, if it assumes the value half, then the 2 points are always on the same surface. Okay, there's no more deformation. You're actually putting the observation point right on the surface, not inside nor outside. Then you get the value of half. Okay, are there any questions so far? So the electromagnetic case is rather complicated. It's written up in my textbook, but the idea is actually very similar. Idea is very similar. You go through using the vector Green's theorem. Okay, you go through using the vector Green's theorem, and then you solve the problem. But before I go on to the electromagnetic case, let me say one more thing. You have 2 sets of integral equations that you can derive from this 2 extinction theorem. Say I can choose to use the bottom one as the equation. Then I will have 2 sets of integral equations for this problem. But then I have unknowns that are monolayer as well as dipole layer. Monolayer as well as dipole layer. So I have 4 unknowns, but 2 equations. And they are not enough to solve the problem. So what do I need to invoke in order to reduce the number of unknowns to 2? We have 4 unknowns. This is A. This is a normal derivative of the potential. This is a potential. This is a dipole layer source. This is a monolayer source. If you know the potential on the surface, do you know its normal derivative? Do you? Detail. If I know this thing, do I know this thing? No, right? No. Because this is right on the surface. I do not know its value away from the surface. So knowing this does not imply that you know this. So these 2 are independent unknowns. This is called a monolayer. This is a dipole layer source. This is a monolayer source. So there are actually 4 unknowns in these equations. There are 4 unknowns, but only 2 equations, because I can get 1 equation from here, 1 equation from there. The other 2 equations are actually redundant because it depends on where you put your observation point. You don't get more equations by using the top or the bottom of the extinction theorem. So I need something else to reduce the number of unknowns to a smaller number. What do I need to do? I need to apply what? Boundary condition. I need to apply boundary condition. For this kind of scalar problem, usually phi1 equal to phi2 on SP. Okay? And then you might have another boundary condition like normal derivative of the potential or the monolayer source on S. Okay? On S. And then with that 2 boundary conditions, you have 2 more equations, 4 unknowns and 4 equations now. Or another way to think about it is to eliminate 2 of the 4 unknowns, and then you get 2 equations, 2 unknowns, and you can solve the problem. And then you can go about finding the matrix representation of this integral operator, just like we did for the differential operator. You obtain the matrix system, and then you can go and solve this problem. Yes?
What are P1 and P2?
P1 and P2 depending on the scalar problem that you're solving. For electromagnetics, it can be epsilon1, epsilon2, mu1, mu2. Okay? But scalar problem never exists in electromagnetics except in 2D. Okay? So to get a scalar problem out of this in electromagnetics, you have to do a 2D problem. 3D problems are always spectral. And then you will get this kind of problem, say in acoustics. P1 and P2 might be related to density, Buck modulus, or that kind of thing. And you might get this kind of problem solving Schrodinger equation, which is scalar wave equation. And P1 and P2 can be the effective mass, or something related to the effective mass of the electron. Okay? And you will have different kind of effective masses dependent on what kind of lattice constants the electron is seeing. Okay, so you have that kind of thing, and so on. And The next thing I'd like to talk about is the vector wave equation case, which is rather complicated, but the ideas are very similar to this. Okay, let's take a coffee break and come back and do the vector wave equation. Or maybe not. Maybe you can also skip that. What do you think? You want me to go through the vector wave equation case, or skip it?